thank the organizers for the opportunity to speak and their wonderful hospitality. Okay. I'm going to be talking about a joint project with Sema Salur at the University of Rochester. And let me start a little bit about calibrations and why they're wonderful. Okay, so I'm going to assume throughout that M is an n-dimensional Riemannian manifold. And definition, a calibration on M is a closed P-form phi, and I'll denote the space of P-forms on M by omega, such that phi evaluated on E1 up to EP is less than or equal to 1 for all orthonormal E1 up to EP in the tangent space at some point. Okay. So if I let big E denote the span of these P vectors in that tangent space, then we write this condition right here as the statement that phi restricted to any p-plane is less than or equal to the volume on that p-plane. Okay. Let's call that asterisk. Now, when equality holds, star E is calibrated. Calibrated, of course, by phi, but I'll just say calibrated. Then a submanifold, NP, sitting inside M, is calibrated. By phi, if each tangent space is calibrated. Okay? So phi looks like the volume form when it's restricted to our submanifold N. And calibrated submanifolds are lovely because a calibrated submanifold is volume minimizing. In its homology class. Okay. So not just a minimal manifold, but actually globally volume minimizing in its homology class. And the proof is a straightforward application of Stokes' theorem. Using the fact that phi is closed. So let me give you a proof of that. It won't take any time. Proof by Stokes' theorem. So suppose N is calibrated and N and N prime are of the same homology class in M. Then the volume of our calibrated manifold, well, that would be equal to the integral of the volume restricted to N over N, but I know that's equal to phi. So I can shove phi in here. Okay? And since phi is closed, and N and N prime are of the same homology class, Stokes' theorem says this is the same thing as the integral of phi over n prime. But for any p-plane, phi is less than or equal to the volume. So this is less than or equal to the volume over n prime, which is volume of n prime. Okay. Always.
Can you explain the first equality, why volume of n is integral of phi?
Because I could say this, right?
Yeah.
Okay. But n is calibrated, so I have equality here. This is the definition of calibrated. That phi restricts to be the
I
volume.
have no equality on the blackboard.
No definition.
Here.
No.
This is one big long rambling definition. Equality holds, plane is calibrated. So I can just shove phi in here. Okay. All right, so let me give you some examples of calibrations and calibrated manifolds. So a very popular example is the following. Let m omega be a Kähler manifold. So omega is the Kähler form. Then Wirtinger's inequality implies that the kth exterior power of your 2 form, Kähler 2 form, appropriately normalized, is a calibration. Calibration. And the calibrated submanifolds are exactly the k-dimensional complex submanifolds. So that's sort of the first calibration historically. And I'll be talking about the associative calibration. I won't give you the explicit formula for it right now, but I will in a moment. And this is a 3-form phi that we can define on any G2 manifold. So any 7-dimensional manifold that admits a torsion-free G2 structure. And similarly, we have its dual, the co-associative calibration, which is a 4-form on your favorite G2 manifold, or the Cayley calibration. Is the self-dual, let's call it psi. And this is a 4-form on any spin 7 manifold. Okay. Now these 3 calibrations were all introduced in 1982 in a famous paper by Reese Harvey and Blaine Lawson. And they have a very rich geometry, by which I mean the following. Just because you find a calibration on a manifold, that does not mean there exist calibrated submanifolds. Sometimes the collection of planes for which these exist is just too small. Okay? There are lots and lots of calibrated submanifolds for this class of examples. For example, let's suppose that you have a G2 manifold. Okay? Pick any 2-dimensional submanifold. It sits inside an associative submanifold. It sits inside a 3-dimensional manifold that's calibrated by phi. Okay? And there are similar results for the co-associative and the Cayley calibration as well. And their geometry is also algebraically just beautiful. It's related to the quaternions and wonderful, wonderful structures. I'm sorry, the octonions, not the quaternions. Wow. The complexified quaternions, of course, is what I meant.
Can I just ask
Sure.
a question?
By G2 manifold, you mean G2 is acting on the manifold?
No, I mean it emits a principal G2 bundle. And I will go through the definition correctly because it's important for the result that I'll state. So please put up with that vagueness for the moment. All right. So let me specify to the associative calibration. And we'll start on my favorite G2 manifold, which is Euclidean R7. So let X be the usual Cartesian coordinates on R7. And I'm going to use the shorthand notation that dxij is the two form, dxi wedge dxj, and similarly dx, oh no, I'm not going to use that one. Oh, I will. dxi wedge, dxj wedge, dxk. Then the associative calibration on R7 is defined as follows. It's dx 1, 2, 3 plus dx 4, 3, 1 wedge, dx 4, 5 plus dx 6, 7 plus dx 2 wedge, dx 4, 6 minus dx 5, 7, and finally minus dx 3 wedge, dx 4, 7 plus dx 5, 6. And it's not too hard to see working with this that, for example, this is a calibrated plane, by which I mean that span del del x1, del del x2, and del del x3 is a calibrated plane. So you could think of that as a standard example, or if you imagine that you're sitting in the imaginary octonions, these calibrated planes are the planes that are closed under an alternating under a cross product. Well, yes, that's what I mean. They're a cross product defined on the imaginary octonions. Okay. Now, G2 is precisely the set of linear transformations on R7 that preserve phi naught. And this sits inside the special orthogonal group. This characterization of G2 is 87? Yeah, 1987 by Bryant in that lovely, exceptional Holonomy paper. Holonomy paper. Okay. So that's the compact group we're going to be talking about for the G manifolds. Now let me tell you what a G structure is, or how I'm going to interpret a G structure. So assume throughout now that M is a 7-dimensional manifold. Okay, so this will be our generalization of R7. And let's start with F over M, which will be the frame bundle of linear isomorphisms. U from the tangent space at a point of M into R7. Okay. F is a right GL R7 bundle, principal bundle with action given by U dot A is defined to be A inverse composed with U. So that's a G2, a GL7 bundle. We're interested in a reduction to a subbundle that has fiber group G2. So, definition, a G2 structure on M is a reduction. Let's call it P, sitting inside F, is a bundle reduction to a bundle with fiber group G2. Okay. Not necessarily integrable at this point. In fact, that's what makes this problem kind of interesting. And let me call this the projection from the principal bundle P down to M pi. Okay. Now, note the following.
So I have one question. You define calibration as a closed form.
That's
So
right.
If you don't assume it is integrable, how you know that your form is closed?
Oh, I don't yet, but that's okay. I don't. That's
Okay,
very
so
much a
it will be
problem.
an assumption.
Mhm. But I certainly don't have I don't have any form on the manifold yet, but it's coming. Okay? So let me.
If you have a G2 structure, you have those.
Okay, it's mine.
Okay.
Okay. So let me let E naught denote the inner product on R7. Okay? And as Vincent points out, the G2 invariance of both the inner product on R7 and phi naught imply that this G2 structure P induces a Riemannian metric G, which will just be Riemannian metric and three-form phi on M as follows. So the metric G at a point X will just be the pullback by U inverse of G naught, and the three-form phi at a point X will similarly be the pullback of phi naught, where here U is one of the linear isomorphisms from the tangent space at X into R7, which lies within our principal G2 bundle. Okay. Now, in general, for example, if I'd stayed upstairs on the G7 bundle, G and phi would not be well defined, but since we're only taking coframings in the G2 structure, this is all well defined. Okay. So I need, eventually, if this form phi is going to be a calibration, I need it to be closed. So in particular, what I'm going to need is a torsion-free G2 structure. Let me give you a definition of that now. So let's say let P bar, which will contain P, be the 07 bundle. Yeah, it doesn't really matter. Okay, the 07 bundle of linear isometries. Not just isomorphisms, but isometries U from TXM GX into R7 G naught. Okay? So this is just the orthogonal bundle determined by our G2 structure, by the metric it put on the base manifold. Okay? And by definition, P is torsion free if P is preserved under parallel transport. In P bar. So let's assume now, okay, let's say this, and M is a G2 manifold when M admits a torsion-free G2 structure. Now, notice in this case that if P is torsion-free, then you know that the metric is parallel, and by a similar argument, the form phi is parallel. And the fact that phi is parallel implies that it is closed, since the exterior derivative is just the skew symmetrization of the covariant derivative. Equals 0. Okay. And this implies that phi is a calibration on it. Right. Now, we will use, in a moment, the following result of Fernandez and Gray. So, 1982, P is torsion-free if and only if phi is both closed and co-closed, or its Hodge dual is closed. The theorem I want to prove today is the following. Or actually, I won't prove it in full gory detail. I'll just give you the idea of what's going on. Okay. So let N3G prime be a closed, oriented, analytic Riemannian threefold. Okay. Then there exists a G2 manifold, let's say M phi G, and an isometric embedding. I of n into m such that the image of n is an associative submanifold. And I would like to say a little bit about the history of this type of problem, because this is not the first result of this nature.
An associative submanifold means it's calibrated for the associative calibration.
Yes, thank you, thank you. So, and calibrated by phi. or rather its image. So let me break it into two statements. So we have this N3G prime, and I just mentioned that it has an associative embedding into a G2 manifold. In 2000, Bryant proved that any Riemannian 3 manifold satisfying these conditions, closed, oriented, and analytic, also admits an embedding as a special Lagrangian in a Calabi-Yau threefold. Okay. And there are other embedding results in the case that the submanifold we're looking to embed is 4-dimensional, and it has a trivial bundle of self-dual two forms. And Bryant showed that such an object could embed as a co-associative in a G2 manifold. So this N4 when embedded would be calibrated by the Hodge dual of phi. And this is also in 2000. And Sema and I showed that it could be embedded as a Cayley submanifold in spin 7. And I should perhaps mention, if you haven't thought about these G2 and spin manifolds very much, that a G2 manifold is always 7-dimensional, and a spin 7 manifold is always 8-dimensional.
And these ambient manifolds are non-compact?
Yeah, they'll be like germs.
Yes.
Little germs, unfortunately. Compact would be great. Okay, and the reason why we have these self-dual two forms here is because the method that we use to construct these embeddings relies on having a global framing, which we get for a parallelism, which we get for free on a 3-dimensional manifold. We don't get for free on an n-dimensional manifold, but the group structure is such that having a globally defined basis of the self-dual two forms is good enough to cheat our way through the argument. Okay. So let me tell you a little bit now about the EDS we solve to produce this embedding. So, EDS for torsion-free G2 structure. It turns out that the difficult part in this theorem is not getting the embedding to be associative. It's very easy to rig things so that n embeds as the fixed point set for a G2 involution, a non-trivial G2 involution. And this automatically implies it's an associative submanifold. There's very little to be done there. The difficulty is thickening up this 3-dimensional manifold into this 7-dimensional surrounding germ that has a torsion-free G2 structure. So go back to that frame bundle F with the GL7 structure sitting over M, and quotient this out by, so S will be F quotiented out by the G2 action on this guy, which has a general linear GL7 action. Pi hat. Okay. Consider this. diagram. So notice that any G2 structure, G2 structures are in one-to-one correspondence with global sections, pi bar sections, sigma from M up to S. Okay. If I have such a section, I just pull it back up to the frame bundle and there's my G2 structure. Conversely, if I have a G2 structure and I quotient out by G2, I'm left with just a graph over M, section over M. So what I want to know is when one of these sections will correspond not just to a G2 structure, but to a torsion-free G2 structure. So define the usual solder forms, omega, one form on F, which will take values in R7 by theta on V at U to be U pi star V, where V is tangent to the frame bundle at U. R7. And similarly, then define phi hat, which will be a 3 form on the frame bundle. It's by phi hat V1, V2, V3 to be phi naught eta V1, eta V2, and eta V3. Now, similarly, because I'm going to use it in a moment, we'll take Hodge dual of phi hat to be the 4 form, V1 up to V4, defined by evaluating the Hodge dual of phi naught on eta V1 up to eta V4. So kind of the laziest way we can pull these objects on R7 back to the frame bundle. And let me just note that the restriction of phi hat to some G2 structure defines our 3 form phi on M. Now, since phi naught is G2 invariant, this implies that phi hat descends, well, both phi hat and Hodge dual phi hat descends to well-defined forms on S. And I'm going to use the same notation for the forms on S. Whether we're working on S or on F, we'll just call these phi hat and star phi hat. Okay. And moreover, this is just a reiteration of the comment I made over here that phi is the pullback by the section sigma of phi hat. So take phi hat, push it down to S, look at the section that corresponds to your choice of G2 structure, pull back by that section, and that's another way of constructing phi, or equivalent. Okay. But that is an important realization because this implies that sigma, or P, the G2 structure, is torsion-free thanks to that result of Fernandez and Gray, if and only if the pullback of d phi hat is 0 and the pullback of the exterior derivative of star phi hat is 0. So our EBS is the ideal generated. Ideal I generated by d phi hat and d asterisk phi hat. Now, I want to point out something trivial but important because it'll give us a starting point in the proof of the theorem. This is a 4 form. This is a 5 form. And 3 is smaller than both 4 and 5. Okay? Okay, so here is the idea of the proof. So we're going to lift or embed N3 as a submanifold of S. Okay. The lift is a priori an integral manifold of I in S. And again, because the dimension of n is 3, which is less than the degree of the generating forms. It's a priori an integral manifold. Then we have to apply the Cartan-Keeler theorem to thicken this integral manifold, this 3-dimensional integral manifold, up to a 7-dimensional integral manifold. So to thicken N3 to an integral manifold X7 that is transverse to the pi fibers. Okay. That's a loose way of saying there's an independence condition running around in here, and the independence condition is that the integral manifold we construct be transverse to the pi fibers. Okay. Now, this transversality implies that X is the image of a section sigma over pi bar of X over M, and that M will contain N in the construction, and it will be a torsion-free G2 manifold. And let's see. Let me remark that we can control the process well enough to ensure that N is the fixed point set of a G2 involution. Now let me say what that is. That G2 involution will be a map from M into itself such that as an involution, the square is the identity, non-trivial. G2 involution. The square is the identity, and phi is invariant under pullback. Okay. This automatically implies that N is an associative submanifold. All right, so let me give you an idea of how we go through the proof, and you'll also get some hint here of why we, in the four-dimensional case, need that additional structure of a trivial bundle of self-dual two forms. So, sketch of proof. So it is a result of Wu. I'm not sure when, maybe someone in the audience does. It's in Milner and Shafarevich in 1974, that N as a three-dimensional Riemannian manifold, or as a three-dimensional manifold, is smoothly parallelizable. Okay. Now, smooth is not good enough in Cartan-Kähler. We need analytic. And you can invoke a result of Bachner that dates back to 1937 to see that this implies N is analytically parallelizable. So take this analytic parallelization and whack it with Graham-Schmidt to get a analytic orthonormal co-framing. And co-framing omega 1, omega 2, and omega 3 of Ng prime. Now, let's define M naught to be the seven-dimensional manifold obtained by crossing our three-dimensional manifold with R7, R4, and points in here, I shouldn't have used P, I did, didn't I? By Py, where Y sits inside R4. Usual Cartesian coordinates on R4. Then the co-framing omega dy of M naught defines a global section of the frame bundle over M naught. So in particular, I can, using this framing, I can start to think of this GL7 bundle as just being M naught cross GLR7. Okay. And I'll use that identification. All right, now define a lift. This will be F3 from N, and now I'm thinking, now I'm identifying N with N cross 0 inside M naught. Lift into S by F3 P0 is equal to, let's just take the point P0 and the identity matrix. So this puts me up in F under this identification. And I want to be in S. I erased it, but remember I had this projection rho down to S over here. So just whack it with rho to land in S. So X3, is the image, is an integral manifold of our system I. And again, because it's three-dimensional and the system's generated in degrees 4 and 5. And now apply Cartan-Kaler to thicken X3 to a four-dimensional integral manifold X4 such that first let me say this and then justify it because I didn't mention what I need for this, such that it is closed under R and X3 is the fixed point set of R in X4, and X4 is pi transverse. Okay. Right. Then rinse and repeat. And you will just bounce your way up to an X5, an X6, and an X7. I have a couple of minutes left, so let me just say a little bit something about this, since it doesn't make sense. R is a map defined on M, or in a moment on M naught, not on S, which is where X3 lives, and X4. We will define R on M naught to M naught by R of Py is P minus Y. Okay. Now it's easy to see that this is a G2 involution. It certainly squares to the identity. And if you look at phi down here on M, let's call it phi tilde naught on M, it looks exactly like the original phi naught, but instead we have omega 1, 2, 3 plus omega 1 wedge dy 4, 5 plus dy 6, 7, and so on, where my coordinates y start at 4 in R4. Okay, just like the original definition of phi naught. And it's easy to check that R star phi naught is phi tilde naught. And you can lift R to F by just defining R of U to be the pullback of U. In the trivialization, this is expressed as R of Py A is equal to P negative Y R times A, where R is the I4, this matrix. And what's important is that this matrix sits inside G2. And that means that R on F descends to R on S. Okay, and everything commutes beautifully with these pi projections and etc. And so that's how we make sense of this statement here. And it will push back down to that original, that manifold we're solving for, M, which will be the projection of X7 sitting inside M naught. But importantly, containing N. I will stop here.
Thank you very much. questions or comments?